Hi, my name is David Tench. I'm in the Performance and Algorithms group. This work I'm going to be presenting was done with collaborators at Rutgers and Stony Brook Universities. The title of my talk is Dynamic Graph Sketching. So let's say we want to compute a property of a graph that is changing over time. By changing over time, I mean new edges are arriving to my graph and existing edges are being deleted. So nearly all existing systems that process graphs in this way make two key decisions. The first decision is that they write down all the edges of the graph in a big list, and the second is that that list is stored in RAM. And this works fantastically right up to the point when your graph gets so large that you can't fit that list in RAM. So today I'm going to present to you some new techniques we're working on that break both of these rules. First, instead of writing down all the edges, they forget most of the graph information to save space, but they still get the right answer in the end. And these techniques are called sketching techniques. And second, they don't store these sketches in RAM, or they don't need to. They can also store them on disk or across a distributed cluster without sacrificing performance. And the upshot here is this allows you to process bigger graphs than you could otherwise. So let's get started by talking about this sketching technique I'm talking about. I'm going to focus on the case of computing the connected components of a graph. So we assume here that our input is a stream of edge insertions and deletions. We have to find those connected components. So there's an algorithm proposed by Ongua and McGregor in 2012 that allows us to find the connected components with high probability using only n times log cubed n space, where n is the number of nodes in the graph, despite the fact that the graph, if you represented it explicitly, could use up to n squared space. I have a little cartoon here that shows our graph being compressed down by our sketching algorithm represented by a sketch artist, and we can get the connected components back out of that. This is a randomized algorithm, so we can do this with high probability. A little intuition for how it works. We consider the neighborhood of each vertex of the graph. So the neighborhood is all the edges that touch that vertex. And we create a sketch of that neighborhood that's only log cubed n bits in size. And we apply the insertions and deletions to that. And at the end of the stream, we can sample one of the edges coming out of that vertex with high probability. And so I actually have another property that's also very important, which is, let's say we have all these red nodes in this picture here that are part of some connected component. We can take our sketches for each of the red vertices and add them together in a way that doesn't actually increase the space. It's still only log cubed n bits. And now when we query that, we don't just sample an edge adjacent to one of those nodes. We actually sample an edge that is one red endpoint and one endpoint in some other part of the graph. So that allows us to grow this connected component. So that's, in essence, how we solve this problem. Now, if you want to go and actually implement these algorithms, you'll find that there are two primary things that prevent it from being practical. The first is a space problem. While n times log cubed n saves us space asymptotically, in practice this ends up being very large. So for a graph on 1 billion nodes, if you just plug that in for n times log cubed n, you'll get something like 25 terabytes, even before we consider the constants involved. And maybe you want to try to improve the space complexity here somewhat. Well, it turns out you can't. There's a matching lower bound, even including the log factors. So what this means is that this algorithm, even if it saves a space on some graphs, it'll never fit in RAM, at least not for a while, until we get massively larger RAMs. And because it's randomized, you can't just throw this onto disk or onto a cluster and get good performance because you're making all these tiny random reads and writes everywhere. This destroys your performance. So that's our first problem, is space. Our second problem is density. Because our space complexity is n times log cubed n, there's no function of the number of edges here. So this saves us lots of space on dense graphs and not that much space on sparse graphs. In fact, sometimes for sparse graphs, it can be larger than just writing down all the edges. And this bumps up against a piece of commonly believed wisdom in the area that maybe some of you have heard, which is that large and dense graphs don't exist in practice, and the only graphs that are large that are actually out there in the world are sparse. So these are the two problems we'll need to solve somehow if this is going to be a useful algorithm: space and density. I'm going to start by talking a little bit more about space. So we solved this problem by coming up with a new algorithm, which we call cube sketch. So you can see in my little picture here, my sketch artist now is a cube for a head. And another technical detail that I can tell you about this is that the sketches that we use to summarize these graph cuts, we can use them to minimize communication because they're much smaller than an explicit representation of a graph cut. Low communication means that if you're running this on a cluster or on an SSD, you're minimizing the amount of data you need to send over your costly channel. So the idea here is that we're not smaller than the original sketching algorithm, because we know that we asymptotically cannot do that. Instead, we just use less communication. A little hint about how this works. I have my cartoon from before about this idea of vertex sketches allowing us to compress information about a graph cut. Well, so connected components is all about sampling edges across cuts to grow those components. So rather than sending all of the edges uncompressed of a cut across these costly channels, we just send a much smaller sketch instead. And so this allows us to save a lot of communication. In fact, we're able to compute connected components in basically the amount of data transfers it costs to just sort all of the edges in the graph exactly one time. and this matches the best known upper bound for this problem in the external memory model. So again, I want to emphasize that while we can't make our algorithm smaller, we can make it much more communication efficient. And this means that even though it doesn't fit in RAM, now it'll fit on disk and run quickly, or it'll fit on a cluster and run quickly. At least that's what the theory claims. And it turns out that we actually went then and built this in practice. We built a system which we call Graph Zeppelin based on this algorithm, and it is fast and compact. So it gets something like 12 to 15 million updates per second when you run this in RAM, and is nearly as fast when you run it on consumer SSD, meaning I just went to Best Buy and bought a drive. It's also compact. In one instance, we were able to compress a stream of more than 200 gigabytes down to something like 45 gigabytes. And this doesn't just make things fast when you run on disk. In addition, we built a distributed implementation that can get much, much faster, up to something like 300 million updates per second. So these two key ingredients that sketching gives us, which are saving space and reducing communication, you need both of those to get a practical implementation, but then you can actually do it. And when we compare this system against the traditional systems I mentioned in the beginning of the talk that write down all the edges in a big list and store them in RAM, we see here first on this left plot that these are the amount of space these systems use as we look at larger and larger data sets. The solid line on the bottom is our system. We see that its space usage grows more slowly than the other systems, and it's actually below them for graphs that are already on a couple 100,000 nodes if they're dense enough. And so asymptotically, that means that they're going to keep winning in terms of space savings for even larger data sets than this. We also have a plot here showing the ingestion rate of all these systems as the graphs get larger and denser. And so at a point when each of these systems, their representations are too large to fit in RAM and they go to disk, we see this solid line shows that our system has a little bit of fall off in performance, but not that bad. These other systems that weren't designed for that, they go right to zero, basically, because they're not designed to run on disk. All right, that's all I have time to say for space. I want to switch over to my other problem, which is density. Remember, again, there's this conventionally held wisdom which says that large and dense graphs don't exist in practice. I wanted to check whether or not this was really true. So I made this scatter plot, which is all of the publicly available graph data sets on the network repository website. Each of these orange dots is one of the data sets. X-axis position tells us how many nodes. Y-axis position tells us how many edges as a proportion of all possible edges. So we see that when we have graphs that don't have many nodes, they exist at a variety of sparsities. But when we look at graphs with lots and lots of nodes, they're exclusively very, very sparse. So this lines up with the conventional wisdom, but I want to propose a different interpretation of this data. So no more Plato. Actually, it's me now saying that this is a selection effect. I've drawn this black line here. Everything to the left are data sets which we can represent as an edge list using less than 16 gigabytes of space, which is, I just chose semi-arbitrarily as the amount of data I had on my laptop as a grad student, or the amount of RAM I had on my laptop as a grad student. Everything to the right or above this would be graphs that are too large and dense to fit in that space. So those are inconvenient to work on. And the convenient ones are the ones we see. So the question that's natural to ask is there anything in the inconvenient region? And we actually are starting to find some of these applications. I'm going to briefly describe one of them, which is called a bipartite projection method. So let's say that we have a bunch of politicians, and we want to infer their political relationships. But we can't just ask them that directly. They might not tell us the truth. So instead, we're going to try to infer it via some secondary means. In this case, we're going to look at who has co-sponsored bills with who. So this is a bipartite graph. And via a projection I don't have time to explain, this is projected down to a graph over just the politicians that somehow represents inferences about their political relationships. So it turns out that this projected down graph is actually very dense. And so when you're studying problems that are large enough for this, the existing methods end up with this large and dense graph that they don't know how to process. And so they just kind of have to give up or use very coarse methods. This doesn't just apply to politicians. This applies to anything where we have entities that have relationships we'd like to know, but they're hard to observe directly, and instead we infer them through an intermediary. So another example is maybe on the right side here you would have genes, and on the left you would have tissue samples in which those genes are co-located, and you're trying to infer some sort of relationship about them. So the point here is we know of some graphs in this inconvenient area, large and dense graphs. We just lack the tools to study them up until recently. So I have a couple takeaways I'd like to leave you with. The first is these sketching techniques have two benefits. First, this lossy compression idea that we throw out graph information and we can still get the answer if we're careful. And the second is that we can use them to get low communication. And we need both of these things working well to handle massive dense graphs. And the second takeaway I'd like to leave you with is that these dense graphs do indeed exist. And so we're looking for more applications because this is a new technology, and prior to this, people didn't think they were able to do this. So far we know how to compute things like connectivity and minimum cuts. We actually have systems to do these. We have some other targets we'd like to mention, like spectral sparsifying and correlation clustering. But if anybody has applications and they want us to figure out other stuff, we're very interested in knowing about that. So the point here is sketching massive graphs is feasible today, and I'm excited to see what we can accomplish with it. Thank you.